Well, here we are at electrolytic cells, which is the very last topic that we need to do for our standard level content. There will be this video and then one short video with some little exceptions to the rule as we go through. So let's get started. So with electrolytic cells, we're looking again at a electrochemistry situation. So where we're looking at electricity and chemistry and how they work together. The important thing here is that we need to be able to compare and contrast these to voltaic cells. So we are looking for the differences and how we go about using these and what they're used for. So electrolytic cells, these are our main points that we need to cover. They do use convert electrical energy to chemical energy, causing non-spontaneous reactions. Just note with this one, this can be a little bit confusing, but in this case, we still have red cat and anox. Oxidation is still occurring at the anode. In an electrolytic cell, it is positive, and the cathode is negative. We need to be able to draw these cells, explain how the current is conducted within the electrolytic cell, and then distinct between the electron flow and ion flow, and the deductions of the product in the electrolysis of molten salt. So let's get started. So with voltaic cells that we've just learnt about, the whole purpose in a voltaic cell is we're harnessing chemical potential energy to produce electrical energy. So we're using chemical reactions, in particular redox reactions, in order to generate electricity, hence things that act as batteries. In the case of electrolytic cells, what we're doing is the opposite process. We're essentially reversing the reactions that we see in galvanic cells or voltaic cells, and now we need to put in electricity in order to make these reactions happen. So if we look at this with a voltaic cell, what we're doing is we're taking this chemical potential energy, and with a spontaneous reaction, okay, one that goes without us forcing it, okay, we will generate electrons which we can harness and create electrical energy. In the case of an electrolytic cell, one key thing is it's a non-spontaneous reaction. This reaction doesn't happen unless we force it, and we're going to force it by pushing electrons into the cell to make them cause the process that wouldn't normally happen. Okay, so let's have a look at that. This is the setup of an electrolytic cell, and hopefully you will notice, one of the first things you will notice is that it is in one tank. There is no separation of half cells. Okay, there's no separation in an electrolytic cell. Okay, the reason we don't need separation is because the reaction is non-spontaneous. Okay, which means that if we put the reactants together, nothing's going to happen. Okay, in the case of a redox reaction, we well know that based on the reactivity series, if we put the reactants together, they would just react. We'd form a precipitate, have an exothermic reaction generating heat, and we wouldn't get any electricity. So we have to separate those apart. For an electrolytic reaction, there is no separation. Okay, we do have two electrodes. We have an anode and a cathode, noting that this time our cathode is negative. Its polarity changes. Okay, reduction still occurs at the cathode, so red cat still applies. Okay, absolutely, reduction always occurs at the cathode, and oxidation is occurring at the anode. This time, our polarity has swapped to positive. So in a voltaic cell, where our cathode is positive and our anode is negative, they swap polarity in an electrolytic cell, which is very important. And the reason they do this is, if we think about, we talked about our anode as our source of electrons in a voltaic cell. In a cathode, we actually have to plug it into a power supply. So it's not our reaction now that is going to provide the electrons for this reaction to occur. The power supply is essentially a source of electrons. And what we're going to do is force electrons down into the cathode. Okay, and we're going to attach the cathode to the negative terminal of the battery. Okay, so because it's attached to the negative terminal, it gives it a negative polarity. And essentially what we're doing is forcing electrons down into this electrode, which gives them an excess of electrons, and now reduction will occur here, and we're forcing reduction to occur. The strongest oxidizing agent will always be reduced at the cathode, and the strongest reducing agent will always be oxidized at the anode. So essentially what we're doing is we're forcing things to happen. Now we do this to get some particular reagents. So if you think about things like our very reactive metals of sodium and magnesium and lithium, okay, they're very, very reactive metals, so they tend to react spontaneously. If we tried to make electrodes out of these and then placed a piece of sodium into water or lithium into water, they would spontaneously explode, okay? So it's not likely, and if we look at where these are in the electrochemical series, there's not really a reaction that we can get to have them spontaneously react where they would react before they would react with water. So, and we still need to produce these chemicals. Okay, so we still need to produce these metals. And the only way we can do that is by actually forcing the reverse reaction of an ionic salt. So the electrode is connected to the negative terminal is the cathode, and it has an electrons forced down onto it. The excess electrons then flow into the electrolyte where they are gained by the strongest oxidizing agent, and then the positive terminal takes the electrons away and feeds them back into the power supply connecting the circuit. Okay, it is always important to remember that the strongest reducing agent will undergo oxidation and will lose electrons. If we look at this animation, hopefully it will start playing. Here we go. We can see this is an example of an electrolysis of a molten salt. So in this case, sodium chloride. So what's going to happen is this is our piece of solid sodium chloride, and as heat is applied, it starts to break apart the lattice and the ions are now free to move. If you remember that ions being free to move was a requirement of electricity being conducted for an ionic substance. Now, if we take this liquid salt and apply it in a cell which has a battery attached, what we end up getting is the ions will move carrying the current through the cell. And you can see the electrons are forced down onto the negative electrode here, okay, forcing the sodium to be reduced. And then the chlorine is releasing its electrons along here and then will be, the chlorine's being reduced. Oxidized into the Cl2 gas. They've got these around in the normal, not in the same way for the convention of the cell. But what happens is the electrons come in, the sodium ions are attracted to the negative electrode, which is now our cathode. Okay, so they migrate over, pick up an electron, and we get a coating of sodium metal on our electrode. At the same time, the chloride ions, which are now Cl minus, okay, migrate towards the positive electrode, which is our anode, where they give up their electrons to the electrode. Okay, so the electrons move this way, still moving, yes, this way, because our electrons are moving down from the negative terminal in our battery. Okay, and then these are picking up the electrons, donating the electrons, will react with another Cl minus, okay, forming Cl2 gas, which then will leave the cell and form bubbles at that electrode, okay. So the same processes happen at the electrodes, it's just a different polarity. So the reaction is a non-spontaneous reaction, so we can actually separate them, but we don't have to, okay. So generally in an electrolytic cell, you won't see the separation between the two half cells. So this is our voltaic cell on this side, okay, where our anode is negative and our cathode is positive. The electrons move from the anode to the cathode, generating a potential difference or voltage in the cell, okay, with our salt bridge completing our circuit. In the case of an electrolytic cell, you will see that the half equations are reversed here. So now at the negative electrode, what we've reversed the process that was happening. Now the cadmium is being reduced and the copper is being oxidized. So the polarity of the electrodes has changed. we now won't actually generate a voltage. We need to put in that voltage. That potential difference needs to be equaled or higher in order to force the reaction back in the other direction. Okay, so we need to understand what the products will be for a molten salt. In order for sodium and chloride, okay, if you think about salt, it doesn't react when it's on its own. It's a non-spontaneous reaction. They've already reacted and formed stable ions. Now we want to force those electrons back to where they were. We want to give them back to the sodium and away from the chlorine. Because we're forcing that, we're forcing the electrons to move, we actually need to provide energy. That energy is in the form of electricity, and we're forcing back the endothermic process. So if you think about the forward reaction was exothermic and we went this way, now we need to force it back, okay, like pushing something uphill. So the potential difference, which is what the cell would normally give when it's running as a voltaic cell, okay, to form Na plus and Cl minus, we need to equal that to force the reaction backwards. So in a molten salt, so this is liquid salt, you'll notice there's no water here, we will generate chlorine gas and sodium metal. So the sodium will deposit onto the cathode and the gas will form bubbles around the anode. Okay. This is just another way of showing how it's done in the lab, where we can heat a crucible and place the electrodes in. There is one thing to notice here. The electrodes in a electrolytic cell, okay, are typically inert. Okay, they're inert electrodes, so they don't react. They don't react, and they're not reactive metals, which they were in our voltaic cells. So these are typically examples of our inert electrodes are graphite. Okay, so carbon, graphite, and platinum. Okay, these two are our inert electrodes that we often see used for electrochemistry. Okay, this is just another example of a electrolytic cell. Okay, and this is just noting that the long arm of a battery symbol by convention, okay, is your positive, and the short arm is your negative. So the electrons feed down from the negative into the cathode, then the migration of the ions is what carries the charge through the cell. So the negative ions will move towards the positive electrode and the positive ions will move to the negative electrode. Okay, and then the electrons flow up our positive electrode, which is now our anode, and into complete our circuit. Okay, so just remember, reduction always occurs at the cathode. This is a question for you to try. Okay, so we're going to draw an electrolytic cell representing the electrolysis of molten potassium bromide using inert electrodes. Okay, and we need to indicate the polarity of the electrodes, the anode and the cathode, oxidation and reduction reactions, and oxidizing agent and reducing agent species. Have a go at this and then come back and have a look at the solution. Okay, so hopefully you have drawn our key points. The cell being only one compartment. We have the two electrodes. They will be inert electrodes, so you could have chosen carbon or platinum. Our electrolyte in this solution case is going to be potassium liquid and bromide liquid because it's a molten salt. We have the long arm being the positive, the short arm being the negative. Electrons will flow from the negative through down into the cathode, which will now be negative. Potassium is going to be our strongest oxidizing agent, so it will go to potassium liquid. And then bromide is going to be our strongest reducing agent, so it will go to bromine. So we will see a brown liquid forming at the anode, and we will see potassium being deposited onto the cathode. Okay, so hopefully you had a look at that. Read through this solution here, and I promise we will be doing some more examples of these when we get into class. Okay, good luck.